11, same room, 11 p.m. goes to 1:30 p.m. Right? So, what is epitaxy and what do we achieve with that? And then there is a special class of wafers called SOI, which are used in devices, which we call it SOI technology. So we look at that. So epitaxy is a growth of a crystalline film on the surface of another single crystalline substrate. So it's important that your substrate on which you want to do epi is single crystalline, because it will take the lead from that single crystalline substrate to build on top of that. So it can be same material grown on same material, silicon on silicon. It can be another material grown on other material. So in which case you will get lattice mismatch. Right? So we call it homoepitaxy or heteroepitaxy, and that can be silicon on sapphire, germanium on silicon. So there's many different combinations that come in to get that different materials. And the application of these is mostly in what we call HPTs. What is HPT? Heterojunction. There are many junctions in that. Let's say transistor. It's a bipolar transistor, but it has junctions which are made up of many materials built up on top of that. So that lattice mismatch is an important parameter in the growth, because when they're mismatched, they're going to be a strain at the interface, and that strain can result into defects. So there can be number of types of defects. And those defects, strain, as long as there's no defect, is good. It will increase mobility. But when you have defects, what do those defects translate into? Traps. And what do traps do? For rats, they trap them. So in this case, they capture what? Charge carriers. So it's good. So we have changed our language. Instead of saying electrons, we say charge carriers, because it can be hole or electron. So how do we get rid of those issues of strain? We have to make the epi layer to be thick. So when we make it thick along the y-axis, we lose that effect of that strain. So at some distance, the single crystalline comes out of the strain. So that's what we have to do to make it thick enough.
How does thickness help?
Thickness help?
Yeah, how does it reduce the strain?
Because when you go away from that interface, the effect of the strain reduces on the atoms which are.
Oh, I see, because you don't want the junctions. The junctions just are there because you're growing something else.
What junction?
You're not.
Traps.
Yeah.
It's dislocation.
So these are above. They're not a feature.
These are what?
They're not. Those junctions are not what you're trying to achieve.
We want to achieve those.
I see.
So one way is you make it thick. So further away from the interface, you would lose that stress. Or you can make the material to be graded in concentration. It's not concentration, that's what you call that. Sort of an alloy. So you make the 7 in silicon germanium, you can make 0.7 of silicon and 0.3 of germanium, and you can go further away and you would completely change into germanium. So you have what you call a graded junction. So in graded junction, then there's no immediate change in the lattice constant. So it gradually changes to what you are. So that's to reduce the dislocations, the traps. There's different ways how we do epitaxy. So liquid phase is where we melt the silicon and we refreeze it. And when we do that, we have this gallium arsenide which starts building on top of that. So it's a reaction like CVD, where you have gases which are pumped in, and once they see that crystalline structure, they start building on top of that. But in this case now, the material is still crystalline that is being built up. There's SPE, where we ion implant the layer and we let it grow at high temperature. So it sort of melts it and regrows. So it may not be melting in a solution like where you have a totally liquid, but it would be a surface which would be, the high energy will result into the movement of atoms where they find the place in the lattice. And then there's vapor phase epitaxy, which is the most commonly done, where it's just like CVD. So high temperature, and it gives us a very good uniform layer of epitaxy. It has its own issues. High temperature results into the dopants to misbehave. So two ways, it's called auto-doping and diffusion. Of course, you know diffusion where things, they travel, they would get diffused even further in the devices. And auto-doping is where they would get released from the surface and reinsert from the top, changing the concentration different places. So where do we use that? Of course, bipolar devices, where we have heavily doped N-type and we P lightly dope on top of that. And one can argue, why do we have to grow on top? If you have N+, we can just diffuse it down or implant it down, but we don't get control over the concentration of dopant. So we have to put up another layer and define our own doping concentration in that. And it can also create a buried layer below what we grow on top. Right?
How can epi create a buried layer?
So when you do an epitaxial growth on top, so what is below it, it's buried down.
But that's only a part in the transistor, right? The rest of it is not heavily doped. It's only one small
so
part
that
of it.
that part will be now buried under that lightly doped
So you
material.
grow the lightly doped on the head.
On top of that. Yeah. So you have N+ heavily doped, but now you're throwing single crystalline material on top of that, which is lightly doped. So your heavily doped is now buried in between. It's not going all the way. It's of course a limited depth that has that high
So then how does the
concentration.
rest of the substrate form? Below the buried layer.
That is lightly doped. That is supposed to be oppositely doped, in fact. That's supposed to be, if you have P-type substrate, you make your N-type well to make your devices. That's the CMOS. So you always have the opposite doping in the what you call it, the bulk.
So, but the buried layer itself is formed by ion implantation.
Right.
And then you grow the lightly doped on top
On top of that. Yeah. So yeah, you grow it on top of that. So same case in CMOS, we have lightly doped P-type over heavily doped P-type, P+ substrate. In improved latch-up, you have same material, different doping, so there's no contact resistance. There's very low resistance at the interface because there's same material and they are crystal aligned to each other. Basically, it's self-alignment. Whatever you are building, it's aligning already itself to the structure below. And so these are some thicknesses that we make with epi in different cases. So 50 micron for high voltage devices. So it's a very thick part of the device that is made by epi. So it's a major process. So many times we get the wafers already with an epi film from the manufacturer. We don't have to, right? But generally this is a major step in the process. So if you take a look at that, there is a P-type substrate, and then this whole depth is made by epitaxy. So the whole bulk of device is contained in not in the substrate, but the layer which is built on top of that. Because now we have more control in making different concentrations of dopants in there. And this is P-type substrate, and then you have this N well, in which you have this device, bipolar junction transistor. So now this transistor is different than field effect transistor. Right? Well, not go into the details of physics here, but the idea is that where do we use epitaxy?
What's the difference between N and N plus and P plus?
Heavily doped.
I see.
N is lightly doped, N plus is heavily doped. Do we want to do, okay, what benefit do we get by heavily doping a substrate?
High conductivity?
High conductivity. Is that what we always want?
Not necessarily.
So we want charge carriers and we want high mobility. If you have heavily doped channel, you have much more less mobility.
Oh, really?
But you need carriers in the source and drain, collector or emitter, whichever the case. Collector, emitter for BJTs and source and drain for FETs. So you need carriers, but you don't need too too high of resistivity in the channel region.
Will the resistivity always go down as you dope it, or will it?
It goes up. Oh, sorry. Resistivity goes down, but then it goes up because too much doping results into
Less mobility. Less mobility.
why?
Yeah, too much
Collisions.
Collision. So there is too many collisions now with the source inverted charge carrier. So we have to control where do we want what kind of doping.
So there is a compromise, doping and.
You have to see the mobility plot. It will tell you, okay, towards a range above which it starts becoming. But you want it heavily doped for enough charge carriers, right? But not in the channel, right? So, or for the background, or for the well, you want well to be heavily doped. Also, in this case, so this is N plus. So now your devices are built up within that. Right? So when you have the reversal at this guy, you have the channel formation happening there with P-type substrate with the B holes.
But the purpose of the buried layer is to decrease the collector resistance, right? So if you heavily dope it.
Right. Okay. Resistance, when we say epi, we are talking about two materials. The resistance between them is minimal because it's the same material. It's just one is heavily doped, the other is lightly doped. Instead, if you have another material, the interface will become a resistive element in there.
Okay.
So we are talking less resistance is you are making a material on top of another material. So since it's following the crystalline structure, there is essentially very less resistance between two materials.
Okay. So, right. Yeah, because in a MOS, the channel is different from the source and the drain. So you would not want that to be heavily doped because then that would add to the resistance.
Right, right. But channel is always you form it by inversion. So you have too much background is good because now you have much more control over channel formation. Okay? So it's going to switch off only when you go above threshold.
Yeah.
So that's also a benefit why you want it heavily doped. Right? So how does it progress? So just like CVD, we have these products of reaction which get to the substrate, and then once they get absorbed, they travel. They travel and they find what we call terrace. So this is a terrace which is growing. And they get to the edge and start heading up to the growth of the terrace. So this growth is different than nucleation growth, right? Where we with the poly material or amorphous material, they grow differently. They have nucleation sites where there are small islands and then they grow there and they catch each other and they form a film. In case of epi, it is a terrace which is following the bottom substrate and growing. But they can be defects, they can be nucleation also. But then it's the question of how do you control your process to reduce the nucleation. You don't want them to stick somewhere else and cause formation away from the terrace, right? So, but this can happen. The three can come together and form another island away from where they're supposed to be. So the condition have to be tuned to allow enough add atoms to get to the terrace and be the part of the terrace only. So there are then three types of atoms: very mobile, less mobile, but energetically favorable, and most energetic favorable, least mobile. Least mobile are the ones which cause the kink position, which is called C here. So they are resulting into this defect in the film. Whereas A are the ones which are falling on top of that, and B are one which are falling. So these are the one which are showing the defects, A, B, and C. So we have to tune the conditions. So most of the add atoms, they get to the terrace and form part of it. So different recipes are used for silicon: TCS, silane, siltet, and of course, just like CVD, growth rate depends on what recipe we use, what's the temperature, what is the fraction. Fraction was the word, not the concentration. So fraction of material, how much of which one are using, and what's the pressure inside. So we use hydrogen for reduction as well as to dilute. What is reduction reaction?
In which you will want oxygen.
Gain of what?
Electron.
Gain of electron. So, yeah, so it's a gain of electron means it becomes
Negative or
Right.
charged. Used.
yeah. So it's the reaction kinetics are same. It's mass transport limited or reaction rate limited. So high wafer temperature gives us dependence on only the mass. How quickly can we transfer the mass? Because reaction will continue whatever gets it. Or low temperature gives us thermally activity. So these are important factors for us to know. If it's high temperature, then how do we control the reaction? If it's low temperature, then how do we control the reaction in that case? So in both cases, we see that with temperature, the growth rate increases. Right. So again, this is 1 over T, 1000 over T. So with temperature, your growth rate increases. So yeah, these are the real numbers which are shown. For all the recipes, this is always increasing. And there is a transition from A to B, where from high temperature, the reaction becomes only mass transport limited. Right? So if you see a plot like this, you should be able to differentiate what's happening with temperature. When temperature becomes too high, it's only mass limited. How much you can pump in, how fast can you pump in the gases, what is their fraction. So it's not only the pressure, which is how fast you can pump in, it's the, what else? Fraction. Fraction of the reactants, and third thing, quantity, right? So pressure will tell you how much you are pumping. Your fraction will tell you the relative quantity. And dilutant, you would use dilutant to slow down the reaction or make it fast, right? So these things, three things are important in a recipe. And then of course, what are your reactants and your product? Yes.
What is the bottom axis, the horizontal one?
This guy,
Is
1 over T, 1 over temperature, 1000 over temperature in Kelvin. This is your centigrade. These are essentially the same things. So this gives you the Arrhenius plot.
So could you repeat what is the dilutant do?
Hydrogen.
No, what does it do?
It reduces the mass.
So it adjusts the fraction?
Fraction is the relative concentration. Dilutant is overall, both of those reactants, or 2 or 3, how much the overall volume gets into there. So with dilutant, you can control the mass transport. You can reduce the rate of reaction. Right? So this way it is the reaction rate limited, that way it's the mass transport limited, because your temperature is high enough that reaction is almost flat, saturated. Right? So much information comes out of these plots. What happens is we have vapors of silane and rate with. So there's still exact reactions are not known, but some intermediary conditions are known. So that's what we can break it down into what possibly happens. And all of these processes can be etching as well. So if they are reversible. So if we are doing deposition, if some factors don't work out, they can go the other way. They can get etched as well. So you can do epi, and at the end of the day, you find nothing deposited. So because these are reversible reactions, so all the conditions have to meet for the deposition. Right? So this is the deposit zone. So once the concentration is increasing, you get deposition happening along the center bond. Yeah, so under the proper condition, the etching would happen, and what's this plot? Let me see. Yeah, this is showing that with temperature, your reaction becomes almost, your deposition becomes flat. So it becomes only, it's essentially same thing, it's only the how much mass you can transfer inside the substrate. Now, when you say the growth rate and mole fraction, so this is the fraction with each other. So within the growth regime also, the fraction will define if you get a poly material or amorphous material. Right? So not only, so these are all the process parameters. Pressure and temperature on top of that. Fraction and temperature. So if you have too much of this guy above this, then instead of growth, it starts etching. The reaction starts going the other way. Yeah, these are all reversible reactions, right? So just double arrow to break that. So what are the recipes? We get range of growth rates depending on what temperature we use, right? So if you see it within 40 degrees Celsius, we have almost 5 times increase in growth, right? So, but then going too fast, trade-off is the quality of the film, right? So have to see what temperature gives you what growth rate, and then they have different application depending on what do you want to do with that. So this one is the best, which gives you low defect density. That's why it's used for what a process called selective epi growth. So selective epi growth is where we grow only at specific places, and we'll see how do we do that. So if you have silicon dioxide and you make openings in that at specific places in specific shape to reach silicon, your epi will occur only where the silicon is exposed, right? At the end, you can then etch your silicon dioxide away. So that's called SEG.
So I think some confusion. So in silicon epitaxy, do we need chlorine always, or vice versa?
They're different recipes. So these are all recipes for silicon. So you have silane also, which can give you that. So this is
okay. So previous slide.
that was for SiCl4. So this was only for reaction for the SiCl4. right?
Yes.
And this is for silane, right? So there are different recipes which go through different reactions, and their growth rate and temperature requirements are different.
Do we do anything to get rid of the chlorine?
The product has to be treated before you can't just throw it out in the air.
No. I mean from the reaction, like.
Yeah, so you need chlorine incorporated there or not? You don't.
You don't.
It goes away in gas form, isn't
Yeah,
it?
but do we do something to facilitate? Like in RI, we use chlorine to get rid of the intermediate products, right? So we do
Right.
something here to get rid of the chlorine,
No.
or it's not required.
I think it's coming off as HCl, as a gas, acetic gas. You just sweep it away. It's not only that, we have to do doping also while we are growing. So there, again, diborane, phosphine, arsine. We looked at it for the doping of polysilicon. So we can use these to get the film already doped once we get it, right? So then we don't have to do the implantation afterwards. But once we do that, it can happen that at high temperature we get two processes, which is autodoping and out diffusion. Out diffusion is they would start growing in the other directions, and autodoping they would go out and then dope at other places where they are not supposed to go. Right? So the deeper you go, the different is the process. The deeper you go, then it's the out diffusion that happens. If it's close to the surface, then it's the auto diffusion that happens. So it's high temperature process, so you'll have your diffusion to go places where you don't want them. How do we manage this? We cater for this in the process. So when we do diffusion, we would know how deep you want to take it, because if you are doing epi later on, you would know this is going to result into out diffusion, right? So then you can cater for it in the original diffusion or implantation. and they can, so this is contamination where dopants from substrate can stick on the walls and on the tool and get reincorporated into the film. The same way for the other ones. How do we get rid of that? Use the least temperature that we can. So then this would take us to those different recipes. So which one would I prefer then? So I would want to go down in temperature, but then I have issues with disilane, which is toxic and burns, which can be dangerous to handle. So these are all things that we can do to get rid of. Then we can use dopants which have low vapor pressure and diffusivity, so they can get incorporated easily. Seal back of wafer of heavily doped substrate with silicon or silicon nitride. Ion implantation for buried layer and keep them below surface. So when they out diffusion occurs, they would get to exactly where we want them. Or we cap it. Once we do the layer, we cap it, we remove everything, and then we grow it again. We again stop the process, we remove everything, and so in that case the epi would occur in steps. So you do your growth, and then you remove everything, and you stop it, then you remove everything, then you grow. So these are steps you do. Of course, don't have to tell you this. We have to clean our wafer to reduce contaminations. So that's before we start. We can get rid of defects, because if we don't do that, then we have incorporated defects. What are two common defects? One is dislocation, which of course comes from the mismatch of lattice, right? And it can be a relief of that stress, which results into a dislocation and a void. Or this can be due to heat that is coming from the process that we do. It can be because of they are stacked on each other, so that can travel along the vertical line, resulting into a crack type of defect. And they can be either because of impurities, particles, or silicon dioxide regions, because it's a high temperature process. So these are what are used in an area called strain heterostructures, where I think one of you talked about it later, but where we deliberately make them in stress to increase mobility, but we don't want to get dislocations. So what we do is we make graded junctions. We have the quantities change over height, right? So as you go away from the interface, you get to change X and get to your material that you want. So how can we get rid of these defects? We prepare it well. We don't provide thermal stresses. We do gettering. Gettering is using up material and sucking it out. So gettering is a process where we do oxidation. So whatever material we want to get rid of would bind, would react with oxygen and become a species that we can remove. Right? So that's called gettering. And strain buffer layers. So we provide these buffer layers which would sort of buffer or take away the strain from those layers. And those are real things. You can visibly see them. They show up to be in this dislocation physically show up. So this is a line. Sorry, I put my line on top of that. So this is a line which you see on silicon germanium, which is coming because of strain at the interface. In this case also, you see those lines which are built up. So these are defects, the physical defects. So by the way, if you look at these pictures, you can tell your friends that we can see atoms now. Right? So this is from 2008. And here again, they are under stress and they are causing those lines to be. So if you see this line and this line, they are away from each other. So because of this dislocation, they are not really straight. So on this side and this side, see the crystalline structure has, because of stress, has gone out of proportion. So these are defects which we see during growth. So many times we have to do heteroepitaxy. What was heteroepitaxy?
Growing on a different substrate.
Different material on different substrate. Mostly done in HPTs. Right? So we have germane to grow silicon germanium. So XY is the flow rate between those two. And it's done with UHV CVD, RT CVD, or MBE, molecular beam epitaxy. So they all have their own pressure ranges, and the precursors are different for all those processes. But what we want is silicon germanium, which is commonly used in HPT. So this is now telling us what happens to band gap. So okay, the strain heterostructures or strain engineering is also called band gap engineering. Why do we call it band gap engineering? What is band gap? Right?
The amount of energy you have to get to inside an electron is that.
Right. So for a charge carrier to jump that forbidden zone, right? We can change that when we do strain engineering. When we have materials in different fraction, we can change the band gap of that combination. So this is what tells us that once you go from indium antimony to gallium antimony, your band gap is changing. So this is your band gap electron volt. So from somewhere around 0.18 can go to close to 0.8, right? Which you can't do for pure material. But with this, with epitaxy, you can grow material in different fractions and change the band gap. Why band gap is important?
Because it defines the reference voltage.
It defines?
You can use it for as a reference voltage, or it defines the energy you need to impart to the electron.
What do we call that energy? What is it called for the outside world?
Built-in potential.
Threshold voltage, right? So we can change VT, threshold voltage, by changing band gap. So this is an interesting plot which for two different materials, indirect band gap and direct band gap, tells us what is the band gap energy, right? You guys know what is indirect band gap? Don't want to go into that. There's for simple physics in materials, you have those closed, unoccupied molecular orbitals. So you have this conduction band and valence band. So in those, then there are energy states which are lowest and highest in the valence band. Sometimes they are aligned to each other. We call it direct band gap. Sometimes they are not. So now you have energy not only to jump this way, but also to get this way to get to the lowest unoccupied molecular orbital. So simple physics, we have always known this conduction band is valence band, right?
Now, that's great. But could you also talk a little bit about threshold voltage? I think that has something to do with the mass capacitor lab we did, but it's a concept I don't understand.
So built-in potential or threshold voltage is the voltage above which it starts conducting. Your device starts conducting. And silicon built-in potential is 0.7 volts. So most of the time, that's your threshold voltage. So 0.7, in case of transistor, above 0.7, it will be on, below 0.7 it will be off.
Is that why we see that weird curve when we increase the voltage in the mass capacitor, the CV curve?
Right.
Okay. So it's like a
CV
diode.
is capacitance as voltage. I'm talking about conductivity.
No, I understand, but is the semiconductor capacitor we made in the lab, is that a little bit like a diode in that, you increase the voltage and then, the properties change?
Right. It's not a diode, but yeah, built-in potential threshold voltage is more related to diode, where you have PA junction and you have to bias it to make it work.
But isn't there a difference? Like in a diode, you want to go above the threshold. In the mass capacitor, you wouldn't want to go above the threshold.
Right.
Because you're breaking down the outside.
Right.
But the threshold is there for the same reason, right?
No,
it's
you
not.
don't break down outside, but that's your switching voltage.
Yeah.
Above which you are on, below which you are off. So in transistor, you want that to be very clearly defined, so you have the switching effect, right? Up or down. In case of diode, it's just rectification. You wanted to do it in one direction, not the other direction. In another direction, you can go certain voltage and then it breaks down. So that's different concept of breakdown. In that case, it's different.
Yeah, but in case of a diode, it's like a diode is fully functional after its threshold voltage.
After you
in case
go
of a
above.
MOS, it is not functional after the threshold is
Right.
reached. That's how it is.
Yes. Yeah. In that case, it's a different. So you have to make it fully operational above that. Right. So ultimately, it boils down to your band gap energy. Right. So this case, we can change that band gap energy. And direct and indirect has to do with those where do those bands lie in energy diagram. Right. So that's what we call direct or indirect. But the bottom line is that with this going from one fraction to other, we change lattice constant and we change the band gap. Band gap energy change results into different threshold voltage for us. And similarly, this is how thick you have the layer and what is your relaxation of the film as you go away from the surface. So essentially, you want it to become completely relaxed, but it is never relaxed. Not in the range of thickness we are interested in, but we get rid of much of the strain. Right? So increasing germanium gives larger lattice constant, which gives more tensile strain, and lower band gap, which is ultimately low resistivity, high mobility. But there is always cost to do that. So now you have to make much thicker before it relaxes, before you really get to the region that is dislocation free. Right? So this is some example showing that we have to do silicon, germanium, and epi, many different layers. So this is a figure of an HPD where you have emitter, base, and collector instead of source, drain, and gate. So this is what was this? Borosilicate glass film, right? So this is used in that. So many places we don't need to put the epi layer everywhere. We just need where our devices. So what we do is we process called SEG, selective epi growth. We just grow it where we need it. And simple process, we get the silicon dioxide mask and we do our epi. So wherever we have silicon exposed, we see the growth. When we don't see it. And then we can get rid of silicon dioxide. So I'm flipping back to the previous slide. So we don't want it to happen on insulator, right? So we want the whole growth to happen on silicon. So we have to adjust our process. So silicon nucleation is what gives us polysilicon. We don't want that. And it has chlorine, the more the better. It increases the selectivity. But, okay, so yeah, we need chlorine. Yes, you're right. So it's many things I haven't done myself. So this gives us high selectivity, which is where we want the growth to happen only on silicon, not on the insulator. And they also act for diluting the constituents, diluting the gas, reactant gases. So this is example of SEG. The epi equipment are similar to CVD, but there's few things which we need. We need very tight control over the thickness of the growth and ultimately the doping, which we may not be too concerned with in case of CVD, simple CVD. In the film, so all these things are essentially much more stringent requirements than just a CVD film. So don't want auto doping to happen, want to reduce pressure and temperature, so we can reduce auto doping and out diffusion. We want to be exactly same over the whole wafer, so the thickness is uniform and there's no defects at different places because of different tensile strengths. And we want high throughput. So there are many processes are doing a single wafer operation. So this is again an example which is very much like CVD, where you have a barrel reactor where your gas may be coming from the top and going down. You may have a platform where again you give it some angle, you have gases coming in and reactants going out, or you have a plate which is rotating, so your gas is coming in and going out from the other, or one way it's coming from the bottom and sucking out from the bottom as well after the reaction. So it's very much like CVD equipment. So in a typical recipe, when we input the parameters, there are different steps to the process. So once we start, of course, we first heat it up, right? So there's, in any process, in any CVD process, we will have these different ranges of temperature and how long that goes, and what gas starts pumping in at what step. So as a process engineer, we have to monitor all these parameters. So in this case, we are loading a wafer and purging the gas, and then we are ramping the temperature, and once it gets there, we stabilize it, and then probably the gases starts flowing in. And still, it takes a while before we start counting the actual measurement. So once the measurement happens, or the deposition, and once that happens, then again we have to purge. So the whole process needs to be well controlled in temperature, flow of gases, the diffraction of gases and reaction, how fast does it move. Right. So this again example of epi system. So this applied material is probably the largest manufacturer of these high-end equipment. It's a Californian company, Applied Materials. How do we characterize epi films? Can we see the epi growth with an optical microscope? And see
Depends on how much you're growing.
how much do we grow?
0.8 to 50 microns.
0.8 to 50 microns, right? So it's 80 nanometers to 50 microns, a broad range. Right? So we can at least see uniformity of the film with optical microscope. Optical microscopes have a feature called Numarsky. I'll have a slide which gives us a color change if there is a thickness change. So we can look at the colors. So optical inspection, of course, quality and defects and electrical properties are all we know all those standard processes what we can use for this. We can simply see these defects, scratches, and dots and crawlers in the film, and we can see the defect density, and we can see down to 3.5 nanometer change in height. So this is called phase contrast imaging or Numarsky imaging, where we can see. So these are 1.2 millimeter graphite crystals. So we can see the change in thickness. These are these are so-called terraces, different heights of that material. So we can go down to 3 to 5 nanometers to look at the height features from Numarsky. So this is just because the phase contrast, so what you get, the light reflection, if it's out of phase, you can see that difference to 3 to 5 nanometers. It's a good first level of information about quality of your thickness. Or we can do electrical characterization. You guys have done resistivity measurement, right? You can do resistivity measurement for epi film as well. What do we do for resistivity measurement? What do we call that equipment? 4-point probe. What do 4-point probe do? Which two are connected? What are the pairs in a 4-point probe? So we have 4-point probe.
Probes connect to the wafer, the outer two supply the voltage, measure the
So
current.
outer two and inner two, right? Outer two are applying the bias, and we are measuring current in response to that bias. And current would change depending on the resistivity. Right? We can do that to measure this. And then there's a profile in x-axis, in depth, which is called SIMS. What do we do with SIMS? How can we measure the depth profile? How can I measure depth profile?
Spreading resistance.
Spreading resistance. So you measure it from the top.
Yeah. I mean, it's the depth. It's possible to extract that information, correct?
From the top, about the depth. We can cut the wave from the side and measure from the side. Use the probe along the depth. For instance, cut the wafer and have a probe which goes down on the side. Measure the resistivity. Tells you how much is the doping and what depth. Right? Yeah, this is what it is, and then you can measure from that resistivity. You can measure the concentration. So that tells you about the out diffusion. If the diffusion has gone deeper than what you wanted, right? So strain heterostructures are simply made by epi, and what we get is many different types of materials. We can throw strained silicon on top of oxide. So this is like so. This is something which we see that silicon transistor. So this guy is, the channel region is under strain. So this is under strain in this case because they have different materials, silicon germanium on top of silicon, which results into stress there at the interface. So this is ID enhancement, drain current enhancement. So when you have more stress for SOI or silicon germanium on insulator, you have much more enhancement in drain current. So this is enhancement. This is 0.8 times of what you would get with the normal silicon wedge. Now this is enhanced on top of that. So silicon germanium is 1.8, almost double than what you would get from a bulk transistor. Right? So it's almost double enhancement in current. Right? Drain current is what's important for you, how much current you get in the drain. So strain stratostructures, depending on germanium concentration, gives you mobility enhancement factor. So it's 1.6, 1.8, 2.67 even, right? And there is a strain in silicon also. So just look at this guy, just 0.66 strain, percent strain, less than a percent strain. You get almost 2.67 times enhancement, right? So do you understand the importance? Why do they do the strain heterostructures? You can increase the mobility.
What's SEG in that slide you had before?
Selective epitaxial growth. So epi. So this is what we do. Wafer bonding is a process. Before I talk about silicon and insulator, which is again can be made by many ways. So wafer bonding is one of the ways. So this is a process which we do, and we have a new machine here, silicon, to bond two wafers. So essentially, what we can do is we can bring two wafers close in intimate contact, heat them up, pressurize them, they would bond to each other. They would become one. The interface fixes on top of each other. So there are few things which we have to do. So these are just MEMS structures where we bond those structures on top of a substrate and they become one piece. They become part of one piece and they can make moving parts out of that, because now you have this center which is now bonded to the substrate. So in devices also we do that to get different parts made. So we can use an intermediate layer or we can do it directly. Directly it's called fusion or anodic bonding, where we fuse two wafers together, right? Or we provide electrical charges, so they electrically bind to each other, so they become one piece. Or we can have intermediate layer, which would result into thermocompression, alloy making, or soldering. So these are all simple things what we do at macro scale also. Can use polymer again, which would become solidify and bring them into contact with each other. Or we can use glass. So there are different ways how we do that. But the bottom line is we want to make one piece out of it. So what we do in case of a wafer bonder, we have temperature, force. We may be providing it a gas, or we may not be doing that, apply voltage and do it for enough time. We get the wafers bonded together. What we have is can give us nanoscale precision. So you can make devices on both of them, ultimately can bond them together. So we have the capability of aligning it at nanoscale. That's a new machine we have. So in bond chamber, you can use UV energy or plasma to provide energy for bonding. So this is a simple sketch from these guys who provided the equipment was that we have these two wafers with the bond chuck, and you pressurize them from both sides and you heat them, get them together. What do we get out of them? We get a type of wafers called silicon and insulator wafers. Of course, we know one way of making SOI is implantation, right? You implant oxide species, let them go a certain depth, activate them. You have silicon dioxide buried. Or you can oxidize to silicon wafers and bond them. That also gives you the silicon on top, silicon at the bottom, and silicon dioxide in between.
What happens to the crystal structure when you do that?
When you are bonding them,
Yes.
it essentially they merge into each other.
Really?
Yeah.
The boundary is still crystalline? Or is
Boundary is still crystalline. There would be defects, of course, but now you have playing field on both sides. Generally, you don't want to bond them to electrically get something out of the interface.
I see.
But you have now double side of devices.
So you can have a micron thick oxide layer in between, in the middle of the
You
silicon.
can have oxide. Yeah, that is what you do in SOI wafers. So you have silicon dioxide there, which is amorphous and which is now merged. But
I see.
on either side, you have now crystalline silicon.
I see.
So essentially, yes, you're right. You don't want the interface part to be electrically active.
I see.
But what it brings with it is gives you flexibility to work on both sides. And that doubles your real estate. And that's exactly what we use. These all new microprocessors have SOI technology. They're made on SOI wafers. So we make it on top of an insulating film. So having this buried oxide gives us many things. It gives us isolation from the other side. It reduces the stray capacitance with latching up between two devices and improves the radiation hardening. So much less defects because of radiation. Where do we get radiation from? EMI. So sun has this major source of radiation. Especially this is important for space application where there's this whole full-fledged of radiation spectrum that these things are exposed to. So yeah, it's hard to do with simple epitaxy, but what we can do is you can bond two wafers together. So you can what you call a wafer on top of a wafer, you bond it together, and then you break the bottom and you flatten it out. So what you get is a SOI wafer, right? You can use it on top of, so you can use this bulk again in that process to do again oxidation, bonding on top and getting. So this is called smart cut technology or SOI tech technology. So you can make SOI wafers by simple buried oxide or what you call SOI tech. So use hydrogen implant to minimize the material loss. And the other one, implantation is called CyMOX, where you implant oxygen species and you anneal them, they form buried oxide. So you can control this thickness to very fine size. Okay. So in this case, this is called SOI and this is called the handle silicon. Right? Question. What is important now in SOI wafer? Not just the roughness or those things which were important for silicon wafer, but now we are also looking at SOI thickness and buried oxide as well. How thick is this? What is the uniformity? So if you look at it, it's 4,000 angstrom and 50 angstrom non-uniformity for wafer. Right? So then the spec sheet of SOI first has more information than simple silicon. So in this case also we have the thickness and uniformity for that case. Right? Question?
So epitaxy. So I confused terms. So epitaxy deposition, and the deposition which is not the epitaxy. Yeah.
Yeah, so remember, deposition is addition of material from outside world, right? And now there are different types of deposition. You might have chemical vapor deposition, where you have chemical vapors, you do a chemical reaction, and you deposit your product, right? So one subclass of CVD is epitaxial deposition. Difference is epi would give you a deposited material which will be crystalline, right? Now in parallel you can deposit something just physically, which is like the paint shop on this wall. It's a physical deposition, right? You do paint, you physically deposit something. You can remove it easily. It's not chemically deposited. That's what we're going to look at now. Physical deposition is where you have, but in all cases you create vapors, and those vapors get on the surface and they get deposited. You can do liquid deposition also. In that case, what you would do is you will have this liquid thing which you want to deposit, and you would use a chuck like photoresist chuck, deposit it, rotate, let it rotate, give you a film. That's also a physical deposition. Right? But we call it something else. It's not PVD or CVD. Right? So what do we use to deposit like from liquid form directly? You guys have done that already. Sputtering. Sputtering is an etching process.
Oh, spin coat.
Spin coating. What do you spin coat?
Photoresist.
Photoresist.
Diffuser.
Diffuser. Right. You can spin coat glass. So it's called SOG, spin on glass. So you can, and glass will give you something like silicon dioxide, right? So to protect some parts from the others.
So what material do you use?
Silicon on glass, it's molten glass. You spin it, then you heat it up, and then once you heat it up, you take it above glassification temperature. And then it becomes glass. Before that, it's just precursor of glass. Right? So there are, yes, so probably you need to break down different deposition processes and have to go with the terminology. We generally have terms for that, we use terms for that, and those terms mean everything for us. So if I say, somebody say epi, it should tell you what is epi. Right? So epi silicon tell you what kind of process has been used to deposit silicon and what would be the property of that silicon. It will not be polysilicon. Right? And you say I have deposited polysilicon, it should tell you what would have somebody used to do polysilicon deposition. It's CVD. Right? If I say I already have metal and I deposit polysilicon, I deposit oxide, it should tell you then, is it LPCVD I might have used or PECVD? It makes sense? Does it make hierarchical or still it's abstract?
Abstract.
Still abstract. So I'm sorry, you just have 2 more lectures to go, so you have only 160 minutes to make it hierarchical. So what do we do in PVD? We melt our material and let the vapors travel to our substrate. And I don't want vapors to travel here and there, so I want them to travel in straight line. I want to increase the mean free path. Right? What is mean free path? It's time between, distance between 2 collisions. Right? How do we increase mean free path? Vacuum. Right? So I do it in ultra high vacuum. I use special pumps which use liquid nitrogen cryo pumps, which can really create ultra high vacuum. So when I melt it, those vapors have, number 1, they all reach to my substrate. Number 2, they don't have any contamination because I pumped everything out. So we do this in a thing called evaporator, but that top thing is called bell jar. It's a jar. It's a bell-shaped jar. Put it down, And of course, we clean the seal and everything, and then we pump it down. Once it gets pumped down, we have placed our wafer already inside at the top, and we have a crucible, which are small dishes which have pure metal material. Once I get to my vacuum, I start heating it up. Now I can heat it up by just heating coil, or I can use E-beam. I can use electron beam to heat a spot in that crucible. Once it melts, I have a meter, like dosimeter. Basically, it's a crystal. It measures the thickness change as the material is coming out. Once I see stable change in the thickness of whatever is reaching, I open the gate. Now wafer start going to my wafer. I'm measuring how much is getting deposited, so I know my thickness as it is developing. Once I get to my desired thickness, I close the flap, reduce the heat or E-beam, and I'm done. Right.
How do you decide the distance between the material and the substrate?
It comes set by manufacturer. You can't change that.
Okay, so it's not like you can, if you put the substrate lower, you can
No,
collapse through it.
you cannot. It's a standard setup where you just place your material.
A thermal evaporator is part of an example of that, right? The thing that we deposit metal on.
Thermal evaporator is an example of.
Is thermal evaporator considered PVD?
Yeah. Yeah. So it's just physical definition. So thermal or E-beam, the only difference is how you are melting your source, right? Okay. So that's very much different from what you call no, what is that? Choose to deposit.
Sputter.
Sputtering. So very different from sputtering. In sputtering, your target, how do you dislodge your target is different, right? But essentially, again, that is also physical deposition. Right? So in this case, when we have material or we have E-beam that we focus on the crucible, so they go and they can deposit. So at different temperatures, we have different vapor pressure. What is vapor pressure? What do vapor pressure define?
Quantity.
If I have a fluid in a glass, what does vapor pressure tell me about that? When the temperature at which they would start vaporizing. Right. Temperature at which they start vaporizing, so everything vaporizes.
Oh, you can define the boiling point when the vapor
Boiling
pressure
point is slightly
includes.
different concept. The water can start vaporizing way before boiling point.
Oh yeah, but when the boiling point, when the vapor pressure reaches atmospheric pressure, then you have boiling. Or
Probably.
if I remember it correctly.
Okay, hold on.
Sorry.
Water starts vaporizing way before boiling pressure. Way before boiling point. Do you agree with that?
Yes.
That's what we are going at. We don't boil them, we vaporize them. So for aluminum, 1000 degree is where I get something like 10 raised to 12 minus 3. This is the pressure, and this is the temperature where will I get the vapors of aluminum. So I have to pump it down really well. This way, if I pump it down this guy, I can get indium to evaporate at very slow temperature even, right? So these curves tell us what would be the combination of temperature and pressure to vaporize something. And then once I vaporize, I will deposit it. So sputtering is similar process. The only difference is now I call my source as target because I'm targeting that sort of disk to dislodge material that I want to deposit. Right? So I'm targeting beam instead of melting it. I'm targeting to dislodge the atoms in solid form, and then I want them to travel to my substrate. So in this case, what we do is we somehow target this To dislodge, that's why we call it sputtering, because sputtering is essentially means etching, right? So to remove something. So we are sputtering it, and then we have them travel to our substrate. So this is another example of PVD.
Which gives more uniform.
Sputtering. Right? So sputtering is better, but sputtering is more involved. The whole process is more involved. Evaporation is straightforward. Just stick in your wafer, you have. We can control the film thickness much more in sputtering. We can deposit composite materials. We can deposit alloys, which we cannot do with evaporation. So we can have two targets and bombard both of them. Now, it depends on what is their sputtering cost. There's a constant which we have for every material there. And then that ratio will tell us what will be the composition of the deposited material, which one will be more or less. So we can define our composition more easily in sputtering. Targets stay longer because in this case, whatever we sputter gets deposited. In evaporation, you have a big chamber. So those vapors are going everywhere, mostly. They are going almost in the same direction, but you get much more wastage. So if you have, of course, as you progress, you have many spare wafers in time. You can use some to collect some material, which is ultimately wasted. But yeah, so this is less wastage in sputtering as well. But there's equipment is costly, films are less pure, step coverage is bad.
Where does the contamination come from?
You have ultra high vacuum in case of evaporation, but less vacuum in this case. So your vacuum defines how good your other things are in your chamber.
So why can't you have vacuum and sputtering?
We can, but that's an overkill. There's no need of ultra high vacuum in this case. Right? So vacuum is added cost. You don't get to really low vacuum until you pump it long enough. So the longer you pump, the more cost you're adding to the process. Right? So we can clean the surface in situ in case of sputtering, then deposition. So now this is the deposition of sputtering. Dislodging from target, we do it by plasma. We remove those materials and we get them. So now this plot tells us from cathode to anode, we have different quantities of ions and how does voltage change within the substrate. There is a region called dark space, and then we have negative flow, then we have, so ultimately we have our wafer on this side which gets the sputtered material to deposit there. Right? Question? Let's stop it.
I have a kind of random question. When you use 4.0, how does it know if the wafer is P type or N type?
Okay, it wouldn't. Yeah, so it's all tabulated already, so it knows what kind of current would you get for what kind of voltage, at what resistivity, at what. So you know resistivity, but the values, these three values, interpolate to the concentration.
So it's kind of pre-programmed to calculate whether it's P type. That's one thing. I mean, you can get the resistivity, I understood, but I don't understand.
Yeah, but for that voltage and that current, right? Question. I'll see you on Tuesday.